Well, hello everybody. Welcome to Blue Marble Science. So you're having trouble with the inverse square law, huh, Bob? Hey, don't worry. We're going to help you out. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors back out of punching range, and let's light this dumpster fire and have some fun. Hey, Gladys, you ready? Let's get to it. Now, for any of you that don't know who this is Bob Knodel, and he's a pretty prominent figure in the flat earth community. For years now, Bob has gotten the inverse square law wrong. Bob has tried to calculate what the intensity of the light would be at the surface of the moon, and because Bob doesn't understand the inverse square law, he gets a ridiculous answer. We'll show you how to do it correctly, but first, let's listen to Bob.
What I'm going to do is I'm going to play, let's see, where is it? Taboo Conspiracy. Yeah, that's not it. This one's it. Okay, so I'm going to play a part of Ben's presentation. And let me actually stop my screen share and reshare it because I remember I have to do this right this time. So hang on just a second. Share screen, Chrome tab. Share audio. Okay. So Ben, of course, then decided to do a piece on the inverse square of light that he did at, I think it was one of the flat earth and he was out of the country somewhere. I can't remember exactly where it was, but he was out of the country. And so he did the presentation there.
Romania.
And yeah, it was Romania. That's right. Yep. I can hear Ben screaming, Romania, Romania. And so I'm basically, because he explains it so well, I'm just going to let him, kind of talk about it. And then I will show you what I said about it. And we will go on from there. So you understand exactly what we're talking about when we talk about the inverse square of light. So without further ado, here's Ben.
I think it was maybe Jeranism or Globebusters or both who first mentioned this, but this is a terrific proof of the fake moon landings, and it deals with how much illumination there would have been on the lunar surface according to the heliocentric model.
The inverse square law actually doesn't have anything to do with the heliocentric model. In science, the inverse square law is any law that states a physical quantity is inversely proportional to the square of the distance to the source of that quantity. We'll go into this more as we go along.
The inverse square law describes the intensity of light at different distances from a light source. Every light source is different, but the intensity changes in the same way, meaning this is a law for all light sources. The intensity of light is inversely proportional to the square of the distance. This means that as the distance from a light source increases, the intensity of light is equal to a value multiplied by 1 divided by d squared. Here are the simple equations. As an example, if you place a 100 lumen bulb in a floodlight that shines on only 1 square meter of surface, that surface will be lit at 100 lux. However, if you back the floodlight away to shine on 4 square meters, the surface is now lit with 25 lux.
Taboo Conspiracy just provided some information, but no explanation at all about where it came from. So let's see if we can understand this a little better. When we talk about sound waves or light waves, frequently we talk about an isotropic radiator, and that is simply a point source. By point source, I literally mean a point, a singularity if you wish. And that point source radiates energy in all directions uniformly. But before we go any further, let's talk about a couple of quantities that frequently get confused, and it really makes a mess out of things at times. The lumen is the SI-derived unit of luminous flux. It's a measure of the total quantity of visible light emitted by a source per unit time. Lux, on the other hand, is the SI unit of illuminance, or intensity if you wish, and it's equal to 1 lumen per square meter. Now going back to the previous diagram, we can think about a point source and a spherical surface surrounding that point source. The area of a spherical surface is 4 pi r squared. So let's take an example. Let's say that we have a point source of light that produces a total of 126 lumens. That's kind of an odd number, but you'll see why in a minute. If we make our spherical surface a radius of 1 meter, the area is equal to 12.6 meters squared. That means the intensity of light at that surface, at that 1 meter radius surface, is 126 divided by 12.6, or 10 lux. On the other hand, if we double the size of that surface, now we make the surface a radius of 2 meters, the area becomes 50.4 square meters, and the intensity of the light drops to 2.5 lux. This is the inverse square law. If we double the distance to the point source, we are doubling the radius of that spherical surface, and we are increasing the area of that surface by a factor of 4. So that's how the inverse square law actually works.
The full moon, which is supposed to be reflecting sunlight, has an illuminance up to 1 lux on the Earth's surface. That's not substantial, but a full moon has enough illuminance to read from it here on Earth. It is allegedly 376,285 kilometers to the moon from Earth's surface to moon surface. Let's assume our Apollo astronaut is 0.01 kilometers, or 1 meter, above the surface of the moon. We now plug the numbers into our inverse square law equation to find the intensity of the moonlight at the surface, solving for intensity at distance 2. I have the numbers on the printout, but you can see for yourself the problem.
Oh, we see the problem, all right. You're not 1 meter from the surface of the moon. You are 1 meter from the point source, that imaginary point where all of the light from the moon emanates. If you want to be 1 meter from the surface of the moon, the number is 1,738,101 meters from the point source. There's the problem.
Sunlight has an illuminance up to 128,000 lux on Earth. That's pretty bright. That's as bright as it gets. Assuming my math and figures are right,
No.
applying the inverse square law, the Apollo astronauts would have experienced 1,106,175,009,570 times more illuminance on the moon's surface than direct sunlight on Earth.
Oh, good grief. There's a lot of things wrong with this calculation. Let me tell you a couple of things that you've left out. Number one, you didn't make any allowance for the attenuation of light as it passes through our atmosphere, and that amounts to about 30%. Secondly, 1 lux for a full moon is an awfully high value. The number is actually something more like 0.2. But that's okay, we'll leave that alone for now. Another thing you haven't thought about is the albedo of the moon. Only about 12% of the light that the moon receives from the sun is reflected to us. That's nowhere in here either. But let's just straighten out this calculation and see what it would have yielded had you used the correct number. The moon's surface is not 0.001 kilometers from the point source. It is 1,738.101 kilometers from the point source. I'm not going to do the rest of this math. I'll just give you the number. And it is not 141 quadrillion lux. It would have been 48,869 lux had you used the correct figure for the distance of the moon's surface from the point source. I'll do the correct calculation for you in a few minutes. You'll be surprised at how close it comes to the 128,000 lux you're talking about here on Earth.
All right. Now, you guys really need to take that in, all right? Because when I did it, I came up with a figure in the quadrillions of lumens. Now, what Ben is doing differently here is he's comparing it to direct sunlight on Earth. And it's over 1.1 trillion times brighter than direct sunlight here on Earth is what it would have to be, right? So Again, what are some of the arguments they come up with? Well, the first thing they came up with, oh, you guys, you're stupid because that only works for a point source light. That's like, oh, okay, great. So let's look that up. So I looked it up, and let's look at point source. And there's some interesting things about point source light. So it says right here, a point source is a single identifiable localized source of something. A point source has a negligible extent, distinguishing it from other source geometries. Sources are called point sources because in mathematical modeling, these sources can usually be approximated as a mathematical point to simplify analysis. The actual source need not be physically small if its size is negligible relative to the other length scales in the problem. For example, in astronomy, stars are routinely treated as point sources, right? Even though they are actually, in actuality, much larger than Earth. So essentially what they're telling you then is that, yeah, there's a difference, but not really.
This is Houston. Say again, please.
Houston, we have a problem.
Roger that, 11, and the problem is Bob doesn't understand what he read. Bob, the moon is not a negligibly small source of light. It's not like a star. It occupies about half degree of angular size in the sky. We have to account for the size of it in the way that I've just shown you. That's the problem you guys are having with this.
All right, so let's go back to here and share it. All right, so there it is. Okay, and let's look back at the point source. So here's what I was reading right here. A point source is this, just so you guys weren't thinking I was kidding about it. And then I went and I looked up under a photography site, and they were asking about inverse square law and reflected light. In other words, they're basically talking about, well, if it's reflected, now remember, they tell us that the moon is supposedly reflecting the sun's light. Now in the flat earth model, that's not true. In the flat earth model, it is an absolute source light. But in their model, and we're going to go ahead and go with their model, it's a reflected light. But the thing is because the moon ultimately is so much smaller than the Earth, and especially when it only has a 0.52 degree angular size in our sky, that means that we can treat it as a point source light. And this whole thing, I won't go through all of this, but I will put these in the show notes to basically, you can follow the discussion, but what they come to the conclusion as is exactly what I just said, okay?
I checked your citation, Bob, and no place in here does anyone suggest that we should treat the surface of the moon as a point source. In fact, it's absolutely ridiculous to think that you could take something that's half degree in angular size, as you've already indicated, and treat that as a point. But I did find a little bit of interesting stuff through here. And if you go down through this thread to the very last one, it's from a guy calling himself Loki. And he says this, and he's very correct in what he says. For the simple case of a point source, light radiates in all directions. The amount of light can be described in terms of how much of it passes through a spherical shell surrounding the point. Assume the point is in the exact center of the sphere so all areas are uniformly lit. Bob, that spherical shell that he's talking about is the surface of the moon. The point is at the center of the moon. You're just being dishonest about this when you say it supports what you're claiming, because it actually does not.
Then I went to Stack Exchange, right? Physics.stack exchange. This is another major site. So I'll just tell it accept all cookies. And they are talking about, again, it's right here. It says the inverse square law applies to point sources. For extended sources, that becomes accurate at distances that are large compared to the size of the source. At large distances, the source looks like a point. What large means depend on the application. In case of the light fixtures, blah, 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 blah. Anyway, again, but what it ultimately concludes then is that when you are treating the moon, because it's all up there all on its own, and it is essentially a point source light.
And again, you're misrepresenting what's been said, Bob. It does not say that the moon is a point source. It doesn't say that at all. You're just being dishonest.
Now, in the flat Earth model, it absolutely is, because we claim it is its own source. So, and again, it's all in here, and these guys are talking about it. I'm sure they know a lot more than I do about it.
That's the first thing you said that actually makes sense.
But I was simply looking to find out, what exactly the difference was. Well, and think about this, guys, for a minute. So what is the difference, really? If you have a point source light, so if you have, like, say, a floodlight, right? And it's not an omnidirectional source. It's not like a light bulb, but you have a floodlight, let's just say, pointing one direction. And you point a light meter at it and you can get a light source on it. But say I pointed that floodlight at a mirror and then I pointed my light meter essentially at that reflection. Well, it's going to be essentially the same luminosity, right? I mean, depending on how well polished the mirrors are and all that stuff. But it is essentially going to be the same difference as a point source light, right? Even though it's technically reflected. So, and again, because of the distances and the sizes involved, and the fact that it's only a half a degree in our sky, according to all these guys, these experts that are talking about it, they say, oh yeah, absolutely, we can treat it as we can treat things like the moon and stars as point source lights. They said it, I didn't. Okay.
Well, that's exactly ass backwards, Bob. You said it, they didn't. Listen, a moon pie held at arm's length is not a point, Bob, nor is the moon. How big is a point in your world, by the way?
Yeah, exactly.
In their model.
In their model, you're right. And that's why they have to constantly twist everything and make up stuff like, oh, you're measuring to the center of the moon. It's like, what damn difference does that make?
Well, I got an idea. Let's see what damn difference that makes if we actually do the calculations correctly. I said we were going to do this earlier, so let's take a crack at it. Let's assume the distance from the surface of the Earth to the surface of the Moon is about 380,000 kilometers. Let's assume the Moon's diameter is 1,738 kilometers. Let's assume that the albedo of the Moon's surface, in other words, the amount of light it actually reflects, is 12% of what it receives from the sun. Let's assume that our atmosphere has an extinction of about 28% of the light that it receives. And let's assume that the moonlight intensity at Earth's surface is about 0.25 lux. You can look it up and you'll find quite a range, but 0.25 lux is not a bad estimate. So here we go. The intensity of light at the surface of the moon would be the 0.25 lux we can measure here on Earth times 1.28, and that's to account for the extinction of light as it passes through our atmosphere, times the inverse square law, which is 380,000 divided by 1,738 squared, and then that divided by 0.12, which is the albedo of the moon's surface. When we do that, we see that the sunlight intensity at the surface of the moon would be 127,478 lux. And that's very nearly exactly what we measure when we're outside Earth's atmosphere. And by the way, Bob, the next time you decide to tell me I'm wrong in one of these chats, you can assume that one of the two of us is full of shit, and it isn't me. Hey, thanks for watching. Hope you guys enjoyed it. Don't forget to hit the like and subscribe buttons down there. Click the little bell if you want notifications. Shout out to the patrons and PayPals. Really appreciate all you guys do. And I guess we'll see you guys on the next one. Hey, Gladys. We're out of here.